Hi everyone. In this topic, we will go over chapter 4, Models of Software Architecture. Chapter 4.1, that is overview, Models for Software Architecture. Today we are diving into the origins of object-oriented programming languages. While object-oriented programming became widely popular in the early 1980s, its tools go back much farther, starting in the 1960s when high-level programming languages were still emerging. The first notable milestone, Simula 67, this groundbreaking language introduced key concepts we now associate with object-oriented programming: objects, classes, inheritance, and virtual procedures. Fast forwarding to the 1980s, and the programming world saw a surge of languages designed either purely as object oriented or enhanced with object oriented features. Prominent examples include Smalltalk, Eiffel, C, Ada, and CLOS, all of which shaped the modern software development landscape. In this session, we'll explore how these languages contribute to the evolution of software design and development. When we talk about object-oriented programming, it's important to remember that it's only one part of a larger process known as object-oriented software engineering. Object-oriented software engineering is much more broader than just writing code. It encompasses the entire process, beginning with analysis, moving through design, and finally reaching the programming stage, all while following the object-oriented paradigm. It starts with object-oriented analysis, where the goal is to model the system's requirements. This phase defines what the software needs to do. Next, we move on to object-oriented design, which takes the analysis model and transforms it into an architecture or blueprint for the software. This design guides the next phase, code development. Finally, in object-oriented programming, we use object-oriented programming languages and tools to implement the design into actual working code. As we explore object-oriented software engineering, there are three fundamental principles that guide the entire process from analysis to code development. These principles are encapsulation, which involves building the data, attributes, and method that's functions that operate on the data into a single unit known as an object. This principle ensures that the internal workflows or workings of an object are hidden from the outside world, allowing for better control and security. Inheritance. Inheritance allows objects to inherit properties and behaviors from other parent objects. This promotes code reuse and establishes a hierarchical relationship between classes, making the system easier to maintain and extend. And then polymorphism. Polymorphism enables objects to be treated as instances of their parent class. More importantly, it allows a single method to work in different ways depending on the object it is applied to. This flexibility is key to making systems more dynamic and adaptable. You can follow this YouTube video for more detailed insights into these concepts. Encapsulation is often referred to as the information hiding, and for good reason. Its purpose is to separate the interface of an object from its implementation. This separation is essential because it provides flexibility in the design, allowing the internal workings of an object to change without affecting the rest of the system. Let's look at a classic example, the stack. A stack's interface might define two key operations, push and pop. These are public methods available to other parts of the program, but how the stack stores its elements internally is hidden. For instance, the internal structure could be implemented using a linked list or an array list, and no other part of the program needs to know which one is used. The only requirement is that the stack continues to function as expected. This hidden implementation detail gives developer the freedom to modify and optimize the internal structure without disrupting the code that depends on it. Inheritance is a key principle of object-oriented programming that allows new classes to derive from existing base classes. This means that the new class, also called a derived class, automatically inherits the attributes and operations of the base class. For example, if we have a base class called vehicle, a derived class like car can inherit the vehicle class's properties such as speed or fuel, and operations like starting or stopping the engine. The car class can then add its own unique attributes and behaviors like air conditioning or navigation while still utilizing what it inherited from vehicle. This ability to reuse existing code not only saves development time, but also ensures consistency and readability and reliability across different parts of the system. By reusing the implementation of base classes, inheritance improves the effectiveness of software development, allowing teams to build on a solid foundation without having to rewrite code from scratch. Polymorphism is one of the most powerful concepts in object-oriented programming, allowing objects to behave differently depending on where they are in the inheritance hierarchy. In essence, it enables the same operation to take on different meanings based on context. Polymorphism can be categorized in two types. Vertical polymorphism. This occurs when derived classes override operations from their parent class. For example, a base class shape may have a method called draw, and derived class like circle and square can each override draw to behave differently, drawing a circle or a square respectively. And then horizontal polymorphism. Horizontal polymorphism happens when operations are overloaded within the same class. For instance, the class might have multiple methods named print, but each one handles a different type of data. Sorry about that. Horizontal polymorphism happens when operations are overloaded within the same class. For instance, a class might have multiple methods named print, but each one handles a different type of data, like integers, strings, or arrays. This allows the same method name to function differently based on the input. The object-oriented paradigm is an essential methodology in modern software development, providing a structured and efficient way to design systems. Many well-known architecture patterns such as component-based, pipe and filter, and data repository can be effectively implemented using the object-oriented paradigm. By applying the principles of object inheritance, encapsulation, and polymorphism, these patterns become more flexible, modular, and easier to maintain. Understanding these core object-oriented concepts is not just helpful, it's critical for grasping more advanced topics in software architecture. As we move through later chapters, you will see how the object-oriented paradigm lays the groundwork for building complex scalable systems. Now let's look over in models for software architecture, introducing the object-oriented paradigm. So in object-oriented programming, a class is a blueprint that groups together related data and their operations. It defines the attributes and behaviors that are shared by all the objects created from that class. An object is an instance of a class, meaning it is a specific realization of the class's blueprint. Each object has the same structure as defined by the class, but may not hold unique data. Although the syntax for defining a class may vary across different programming languages, the basic structure remains consistent and generally includes three key elements: class name, that is the identifier for the class; list of attributes, these are the data points or properties that describe the class; and list of operations. These are the behaviors or functions that can be performed by or on the objects of the class. For example, in a class named car, attributes might not include color, make, and model, while operations could include drive and stop. In the object-oriented paradigm, the blueprint of a system's design is typically represented using a class diagram. This diagram captures the structure of the system by outlining the relationships between classes and their attributes and operations. To fully describe a system, both dynamic and static descriptions are necessary. Dynamic specification, this describes the interactions among objects. It focuses on how objects communicate and collaborate to accomplish the system's required functionalities through message exchanges. For example, how an object like customer interacts with a shopping cart object in a e-commerce system to add items. And static specification, this describes the relationship among the system's classes. It's the structural or logical view showing how classes are connected, such as through inheritance, associations, or dependencies. For example, for instance, car class may have a relationship with an engine class, representing how the two are related at the design level. Both views are crucial to understanding and designing an effective system like an object-oriented paradigm. In object-oriented paradigm or object-oriented design, Classes can be derived from other classes through two main approaches, composition and inheritance. Just like in relational database theory, classes can have consistency requirements and they form static relationships that define how they interact at a structural level. Here are four key types of static relationship. Composition. Composition defines a strong whole part relationship where one class contains another. The lifetime of the contained object is managed by the container class. For example, a car class might have an engine class as a component, meaning the car cannot exist without the engine. 2. Aggregation. Aggregation represents a whole part relationship that is weaker than composition. In this case, the contained object can exist independently of the container. For example, a library class may aggregate books, but the books can exist without the library. Association. Association defines a general relationship between two classes. It indicates that one class is connected to another, but without a strict whole part dependency. For instance, a teacher and a classroom may have an association where teacher uses classroom but are not tied to them exclusively. Inheritance. Inheritance allows a class to derive from another class, inheriting its attribute and behaviors. For example, a bird class may inherit from an animal class, gaining its properties while introducing unique behaviors. These relationships form the backbone of how classes are organized and interact within a system. You can watch this YouTube link and get more in details how we can code this in Java and more detailed example of composition, aggregation, association, and inheritance. Composition represents a whole part relationship between classes where the parts are tightly bound to their owner. One example of composition can be found in an online order system. An order object may consist of multiple item objects forming a composition. In this type of relationship, the parts, in this case the items, share the same lifespan of the owner, but that is the order. The items cannot exist independently or be part of another composition. This restriction ensures that when the owner class is destroyed, all of its associated parts are destroyed as well. For instance, when an online order is deleted, all the items associated with that order are also deleted. The behavior is typically controlled by the constructor and destructor operations of the class. In UML, composition is represented by a solid diamond arrowhead pointing from the whole class to the part class. In the diagram shown, the order class contains items in an one-to-many relationship. Unlike composition, aggregation is a more relaxed form of the whole part relationship in object-oriented design. In an aggregation relationship, the parts do not necessarily share the same lifespan as the whole, and they can exist independently or even participate in multiple aggregation relationships. Take this diagram for an example. A car object aggregates parts such as front window and engine and tires. Each part can exist independently of the car. An instance of a tire may be used on multiple cars, or an engine could be replaced without affecting the overall lifespan of the car object. In UML, aggregation is represented by a hollow diamond arrowhead, distinguishing it from composition, which uses a solid diamond. In the diagram, the car aggregates multiple parts, but doesn't strictly own their lifespan. This flexibility allows for greater reuse and independence between the whole and its parts. So this is an example. A faculty member can serve as a committee member of multi-part academic conference at the same time. A car's windshield is part of the car but exists independently. In a composition, when an object is destroyed, all its attributes are also deallocated. In aggregation, attributes can be reused by other objects even after the original object is destroyed. In object-oriented design, associations describe relationship between classes. One common example is a relationship between customer and order. In this case, two classes are linked by a place order association, represented by a solid triangle next to association name. The triangle indicates the direction of the association, showing that the customer places an order. Let's examine the multiplicity of this relationship. A customer can place multiple orders, which is represented by the asterisk at the order end. Each order, however, is associated with exactly one customer, as shown by the 1 at the customer end. Additionally, the arrow at the right end signifies a navigation relation, meaning that from a customer instance, it's possible to access all the order instances that are associated with that customer. Dependency is a special type of binary association in object-oriented design when one class depends on another. This relationship means that changes made to one class can affect the other. For example, class X depends on class Y if class X invokes class Y's operation. Class X accesses class Y's attributes. In real-world scenario, consider the shipping department class that depends on the order class. The shipping department needs access to the list of products in the order to accurately estimate shipping cost. In the dependency relationship, changes in order class, such as how products are stored or listed, would directly impact how the shipping department class calculates shipping. It makes it dependent relationship. In object-oriented design, when one class depends on another, changes in the dependent class can have far-reaching consequences. For example, if the order class is recompiled, the shipping department class, since it depends on order, might also need to be recompiled. In UML diagram, the dependency is represented by a dotted arrow line, as shown in the bottom part of the figure. Reducing the dependency in software design is crucial for several reasons. When fewer classes depend on each other, you can modify and recompile code more quickly without needing to recompile everything. If one class changes, you want to minimize the ripple effect that forces multiple related classes to change as well. Reducing dependencies makes the system more robust and easier to maintain. It is common for 2 or more classes to share a large set of attributes and operations. Instead of duplicating code, inheritance provides an elegant solution for sharing these attributes and operations across classes. When class A is derived from class B, class A automatically inherits all the attributes and operations of class B, unless otherwise specified. For example, private attributes in class B will not be inherited by class A, but inheritance is not just about code reuse. It also enables polymorphism, which is a special case of inheritance. Polymorphism allows derived class to override operations from the base class. This means that a derived class can modify or replace the behavior of an inherited method to meet its specific needs. For instance, a base class animal might have a method speak, and derived class like dog and cat can override this method to provide their unique implementations, such as barking or meowing. So there's a YouTube video for inheritance as well, how we code inheritance in Java. So there's a detailed example in this YouTube video. In UML diagram, inheritance is represented by a solid line with a closed arrowhead pointing from the derived class to the base class. This indicates that the derived class inherits the attributes and operations of the base class. If the line is dashed, it indicates realization relationship where the base class is abstract and the derived class must implement its operations. In this figure, we see a customer class as the base class and 2 derived class, regular and member. Both the regular and member classes inherit common attributes like customer ID and total spending from the customer class. However, each derived class manages customer identification differently. The regular class tracks customer using a cookie number through their browser, and the member class uses username and password for identification and registers members receive discount based on their shipping history or shopping history. The inheritance structures allows the system to handle different customer types while reusing shared functionality from the customer class. In object-oriented design, multiple classes may share a large set of attributes and operations instead of duplicating its functionality across classes. Inheritance allows efficient code reuse. When class A is derived from class B, class A automatically inherits all attributes operations of class B unless otherwise specified. This reduces redundancy and makes maintenance easier. Polymorphism is a special case of inheritance that adds even more flexibility. In the figure, we have an American citizen class that defines a report tax operation, which calculates the tax based on yearly income. The operation is inherited by the American lawyer and American professor class, allowing them to calculate taxes using the same method. The IRS class invokes the report tax operation from each derived class to collect taxes. Initially, report tax operations returns an integer value representing the total tax amount. However, the return type of report tax is changed to a floating point value. This adjustment allows for more precision in tax calculation. With this change, the IRS class, which processes the tax information, must also be updated to handle the new return type. This example illustrates the importance of maintaining compatibility across related classes in object-oriented design. Changes in one base class can affect the behavior of classes that depend on it, requiring updates throughout the system. To avoid cascading changes when modifying the report tax method, we can introduce a delegation mechanism. It helps isolate changes and minimize the impact on dependent classes. In the figure, an American citizen tax handler class is created to manage tax-related affairs instead of directly inheriting the report tax method. Both American lawyer and American professor classes reference an instance of American tax handler. Each class, American lawyer and American professor, implements its own report tax operation. However, instead of calculating the tax directly, they delegate the task to American citizen tax handler by invoking its report tax method. The result is then rounded to an integer before being returned. This delegation approach ensures that IRS class, which collects tax, remains unaffected. The IRS interface is kept intact, while the flexibility to change the report tax implementation is preserved within the handler class. By decoupling the IRS from the direct tax calculation, we reduce the risk of cascading changes when the method evolves. Delegation can solve the issue of cascading changes that often arise in inheritance. By using delegation, we gain the flexibility to modify the implementation of specific operations such as tax reporting without directly affecting the dependent classes like the IRS. In our previous example, we saw how introducing the American tax handler class allowed American lawyer and American professor to delegate the report tax method, isolating changes to keeping the IRS interface intact. On the other hand, polymorphism allows for another level of flexibility by enabling the use of base class reference to invoke the correct operation in derived classes. This ensures that even if multiple derived classes have different implementation of an operation such as report tax, the correct one is called at runtime. By combining delegation with polymorphism, we achieve both flexibility and scalability, ensuring the changes in implementation are handled smoothly without disrupting the overall system. So this was it for this class. In next topic, we will see object-oriented design.